The review for Chapter 9 is the review for the deflection of beams. So in the deflections of beams chapter, we only really discussed the very first section of Chapter 9, the method where we solve this by integrating twice and using boundary conditions. So there's a lot more in Chapter 9 that we didn't cover in your particular class. We'll talk about each of these things that we did discuss. So again, we return to our final exam formula sheet, and for that case in Chapter 9 we have one equation that this second order differential equation as moment as a function of x, and then the two material properties, modulus of elasticity and also the sectional properties, the moment of inertia of the particular cross-section that we're looking at. So let's look at the topics that we looked at in this particular class for deflection. For these types of problems, there's a few steps that we have to look at. Initially, we start with a beam with some sort of loading. Step 1, find the reactions. And here it says as necessary. So you'll see in this particular problem, when we have our free body diagram here of the entire beam, so the free body diagram consists of all the forces and moments that they're applied, if any, the reactions at the support, and then obviously dimensions to create finding the sum of the forces and the sum of the moments. In this particular case, we don't need to find all the reactions because we're going to consider some part x to find our equation of moment in terms of x that doesn't include the reaction at B. So in this particular case, you could sum the moments about B to find the reaction at A. And then the next step is, again, your book uses point J. We have the sum of the moments about point J is equal to 0. And then this will yield moment as a function of x. We stick that in our equation here. Integrate once. Integrate once, we get again the slope. We introduce a constant of integration C1. If we have a boundary condition that has a known slope, we can stick it in to find C1. If not, then we integrate it again. This integrating again yields deflection, or y. So this y is based on the coordinate system that we have, y and x. We integrate the second time, and now we have two constants of integration. So if we have no boundary condition for slope, then we may have two boundary conditions for deflection. So we'll see that in the next slide. For boundary conditions, we saw this before. There's a few conditions. We need enough boundary conditions for the number of constants of integration we have. You may need 2. In some cases, you may need 4, or you may need other ones, as we'll see. But the key thing is the boundary conditions are only valid for that portion of the beam where the equation of moment is the same. The deflection is 0 at any point, at any support. So deflection equals 0 means y equals 0. So anytime we have a support, it can't move up and down because of the support, so y is equal to 0. Only apply these, obviously, in the deflection formula, the last one where we have Iy equals something. Slope is 0 only when we're preventing from rotation, but it's also 0 at midspan for symmetrical loading. So if we have a cantilevered support, if we have a midspan for symmetrical loading. So here we have one instance, dy dx or theta is equal to 0. we may have to introduce some extra boundary conditions. So in some cases, we may need to add these sort of artificial ones, y equals y, dy dx equals dy dx. And that's because of the symmetry, and you'll see that in the next slide. Here's two examples. One of them I solved in class. The first one I solved in class. The second one I believe I talked about in class, or at least talked about the idea in class. For the top one, we had one equation per moment along the entire beam. So the moment equation looks something like this. So if we drew the moment diagram, it's a parabola with a concave down shape. It goes up at the support because we have a moment at the reaction. We have one equation, and we have two boundary conditions as shown here. So we can use those boundary conditions to figure out how to solve the actual problem. In the case of this problem 913, depending on the addition you have, there's either US units or SI units, but the idea is the same. Basically, what we end up with is we have a moment equation that sort of looks like this, and the equation for moment is not the same. At each support, we have our deflection is equal to 0. However, we have to introduce these two sort of artificial ones here, that at point A here, that deflection is the same regardless of which part of the beam we're going at, because we're joining at the same point, and the slope is the same at each point. It's not necessarily 0 because we don't have symmetrical loading.